this idea of estimating with finite sums, and one of the last things we talked about in our last lecture was this idea of LRAM, MRAM, and RRAM, and that's just shorthand for the left-hand rectangle approximation method, the midpoint, and the right rectangle approximation method. Well, I just gave you a program for your calculator, which unfortunately I can't show you on this screen, but in homework tonight, they're going to give you a function like maybe 3x minus x squared, and they're going to ask you to use a calculator program. Use the RAM program, all right, to find, and they're going to give you this table, and they're going to say maybe 10, 50, 100, something like that. I think maybe they go up to 500. And then they're going to have LRAM. For some reason, I just can't write today. MRAM, and RRAM, something like that. Okay. Well, this is all with the calculator program. So for those of you that are watching from home, hopefully you have the RAM program in front of you, all right? But the first thing that you have to do is enter the function in your y equals screen. So the first thing you want to do is put into y1 3x minus x squared. So we put that in, 3x minus x squared. I've done that now on my calculator. And then you want to press your program button. And you want to select your RAM program. And it'll come up, say, program RAM with a flashing cursor, and you just hit enter. Now it says f of x equals, and then it's got y1 in input. You do want y1. All right, and hit enter. Okay. And then it says A. Okay, I left something off of my example up there. We're going to be going from 0 to 2. All right, they're going to give you an interval that we're looking at, just like you did in last night's homework. So your A, in this case, would be 0. So you put 0. And then your B would be your other end point, which is 2. And you hit enter. Then it says the number of subintervals. So the next thing we enter the number of subintervals. Well, that comes from over here. On this table, the first one they wanted you to use was 10 subintervals. So we're going to put in 10. And it takes the calculator a minute, because remember what it's doing. It's finding all of those areas of all those rectangles for you.
Nice.
And so it instantly tells you that this is 3.12, this is 3.34, and this is 3.52. Now, the way this program is written on your calculator, you need to hit enter again. And it gives you more information that you're not ready for yet. It tells you the trapezoid rule value, which we will be learning. Okay, that's important. Hit enter again, and that gets you out of the program. All right? So all you're going to do on these tables is you're going to first do it with 10, then you'll do it with 50, then you'll do it with 100, and I think there's one for 500. You need to be patient when you get to these bigger numbers. It might take a really long time. As a matter of fact, don't even do the 500 one, because it will take the calculator forever and a day. Okay? So when you get to this, you don't need to do the 500 one, just do the first 3. Okay, the next thing we need to do is I want to go over a couple of examples. First, let's look at page 270, example number 2 in your book. Page 270, example number 2 in your book. Okay, and on this problem, okay, they give you a function x squared sine of x, and it's on the interval 0 to 3. Okay? And they even give you the graph. Looks something like that. All right? 0, 1, 2, 3. So it says figure 6.8 shows the graph of the function on the interval 0 to 3. Estimate the area under the curve from 0 to 3. Couldn't we do this with our graphing calculator program? Right? Right? And what should you use? We're going from 0 to 3. What should I use for my n? Because they don't tell you what to use. So what should you use? How many? N is the number of subintervals that you're going to use from 0 to 3. Well, obviously, the more subintervals you use, the more accurate your answer. All right? So if I were you, I would maybe start with something like 5 subintervals, and then maybe go to 10, and then at the most, maybe you go to like 30. All right? Because by the time you get to 30, it's going to start getting it very accurate. All right? And so this is, if you see one like this where they say, and now here's the big thing I want you to see. The instructions. This problem said, estimate the area under the curve. Okay, from 0 to 3. They're looking for this. Remember what an integral is. It is the area under the curve. So if they tell you to estimate the area under the curve, all right, then you can use the RAM program. All right, and I'm not going to go through that right now. The next thing, while you have your books open, let's go across the page and look at example number 3. Okay. On example number 3, they tell you to estimate the volume of a sphere of radius 4. Estimate the volume of a sphere of radius 4. Well, you know, we kind of have to, look at this two-dimensionally first. Okay, let's think of this. If its radius is 4, and I was kind of going to slice it, okay, and I was going to slice this thing, you know, of course it's an entire sphere, so of course it comes down here like this, all right? Would you agree that the formula for that circle would be x squared plus y squared equals 4 squared? Would everybody agree that that would be the equation of the circle? Right?
Sure.
Remember the equation of a circle? That this one has a center at 0, 0, right? Normally the equation of a circle is x minus h quantity squared plus y minus k quantity squared equals r squared. Okay, we covered that way back in pre-calculus. It's been a little while. But in this case, my center is at 0, 0, so I don't need those h's and those k's. All right, they're just 0. So, if I want to estimate the volume of this sphere, though, I have to think three-dimensionally. All right? And what we're going to do is I'm going to slice this thing. Okay, remember what we've been using, haven't we been using the rectangle approximation method? Right? Well, now, instead of using a rectangle, we're going to slice the tomato, so to speak. Okay? We're going to slice this tomato, and we're going to wind up with something like this. You know, if I slice the tomato off, just think of a slice of tomato on your sandwich. All right? You're going to have something like that. Okay? So, what about that, the volume of that slice? It's a cylinder, right? So if I wanted to find the volume of this cylinder, volume of a cylinder is pi r squared h, right? Everybody agree? So in this case, though, the radius, isn't this the radius? Isn't that the radius of that slice, right? And isn't that radius just a function value? Okay, this radius is a function value. So what I need to do is solve this thing for y. So if I subtract x squared, I have y squared equals 4 minus x squared. So y, which of course is my function, is the square root of, I'm sorry, it should be a 16. Sorry about that. Of 16 minus x squared. And that will represent my radius, okay? This right here will give me the radius of my slice of tomato, so it needs to go right here. The volume is pi times the square root of 16 minus x squared. That is the radius, okay? Now, what is h, though? H, okay, is this right here. H is going to be the width of my subintervals, just like when we're doing the rectangle approximation method. Okay? So, if I was doing this, if I was going to do this problem, all right, and not drive myself crazy, okay, and let's say I was going to do it on paper, all right, I would probably use the LRAM, you know, kind of idea, which means I'm going to kind of slice this way, right? And wouldn't it make sense to just break it into 4 subintervals? Right? Do one, make them all 1 unit wide. So this one would be 2, and this one would be 3, and that last one, you know, we would get to 4, right? So what would my width of my subinterval be then? 1. Okay? So this will be times 1. That makes it nice and neat. Okay? Now, if I was going to do this very first slice of tomato right here, right? And I was using LRAM, then isn't the x-coordinate 0? Right? So on this first one, the volume would be pi times Now, remember, this thing is squared, right? So doesn't the square root go away? So it's just going to be pi times 16 minus 0 squared times 1. So the volume of the first slice of tomato is going to be 16 pi, right? That is the volume of this first slice of tomato, 16 pi, for this one right here. Now, isn't it symmetrical? So can't I just multiply that by 2, right? Or probably what I would do is I would do all of the slices over here and add them up and then just double it. That's probably what I would do. Instead of multiplying by 2 4 times, I would just add them all up and then multiply by 2 at the end. Okay? So that gives you an idea how to tackle a problem like that. And, you know, I think it would even be acceptable to use the RAM program, right? To use the RAM. What would I put in for my function, though? You would put in this right here, right? That's what you would put into your RAM program. I would put the simplified form in, you know, after you've squared it. So you would have volume equals 16 minus x squared, the quantity, pi. Something like that. All right? And if your subintervals have a width of 1, right, then you can just enter it that way. All right? All right, let's look at page 275, number 16. This is actually one from the your exercise section, and you're going to have some like this one. I'm actually going to get you started on number 16. Okay? The table below shows the velocity of a model train engine moving along a track for 10 seconds. Estimate the distance traveled by the engine using 10 subintervals of length 1 with A, LRAM, and B, RRAM. Now look, don't they give you all of the values for the velocity function? My recommendation on number 16, which you're going to have to do tonight, is to plot those. What is the value at 0? It's 0. What is the value at 1? It's up to 12, right? What is the value at 2? It's up to 22. What is the value at 3? It's back down to 10, back down here at 10. Okay, and you plot all of your values. All right, I'll put one more. What is it at 4? At 4, it was down to 5. Okay, so they give you all the values. You just have to do the work for the LRAM and RRAM. So if I was doing LRAM, let's say, if I was going to do LRAM, okay, well, the very first one is going to be 0. The next one, this is the rectangle for my next rectangle. Okay, that's the height or the length of my next rectangle. What's the length of that rectangle? 12, isn't it? So what? And the subintervals are all 1 unit, right? So it's just going to be 12 times 1, which is 12. And then you're going to do your next rectangle using the left endpoint, and it's going to be 22 times 1, or just 22. And then you're going to do your next rectangle, which is going to be down to 10. And then you're going to do your next rectangle, which is down to 5. And then, aren't you going to add all these up at the end? You're going to do 12. Actually, it's 0 plus 12 plus 22 plus 10 plus 5 plus the other rectangles. Okay? So it's just using the values in the table to come up with your rectangle values. Okay? And we're going to stop there for today.
Can we see